Okay, it's now 8 p.m, so let's get started. Welcome everybody to Astronomy on Tap. This is our June session. So I hope you're all looking forward to the two talks that we have tonight. So as always, we've got two talks for you tonight. Each are going to be about 15 minutes long, and then there'll be 5 to 10 minutes for questions afterwards. We'd like to tell you, as always, we've got the chat going on. So if you put your questions in that chat, we will then be able to get them answered for you after the talks. So feel free to ask questions throughout the talk or at the end of the talk. So our first talk is going to be by Paul Law Chi Yan, who is giving a talk on magnetic fields in star formation. And our second talk is by Dr. Giuliana Cosentino, who is giving a talk on molecular clouds and supernova remnants. So obviously this is a bit different to our normal Astronomy on Tap because this is our online version rather than in the bar, but feel free to have drinks with you at home tonight. And I hope you all manage to have as good a time as we would be normally. And as well as that, we're going to have our usual quiz. So we'll be having this at the end after both talks. So please stay with us for that. And please do take part because there's still a chance to win some prizes. So just a bit of, as I said, we're live on YouTube with you now. And as I said before also, please join us and interact with us in the chat. So a little bit of background about Astronomy on Tap. This is a global outreach thing where we're trying to bring astronomy to you, the public, at home. Obviously, normally it would be in the bar, but so feel free to get those drinks out and have a drink along with us tonight. And these actually have been going for a while. So they started back in 2013, and now they are active in 69 different cities throughout the world. And that includes 21 cities in Europe, as well as in other places in Asia and in the US. If you want to find out more about this, because if you're joining us from a different location and want to find out if it might be relevant in your city after the pandemic is over and we can get back to the pubs, then feel free to take a look at the website online. So who's here with you tonight? Just a bit of an introduction to the team before we get into our talks. So I'm your host or MC, Holly Andrews. So I'm a postdoc at Chalmers University, which is the group running the Astronomy on Tap Gothenburg. We've also got Andri, who is streaming us to YouTube right now. So hope all the technical things are going well there for her. We've got Jan, who is going to be looking after you in the chat tonight and taking all of your questions in and delivering them to the rest of us so we can get them answered for you. And we've got Franz, who is going to present the quiz to you later tonight. As well as this, we have a team of Sandra, Carmen, and Iskra, who all wrote the quiz that hopefully you'll all take part in later. And of course, we have our great speakers that I hope you're looking forward to listening to. So feel free to say hi to all of us in the chat and a big hi from all of us here in Gothenburg. So these are also the other members of the team, as we've got a great team here with Astronomy on Tap Gothenburg, but obviously these are the other members of the team and also doing other stuff behind the scenes and helping out. So just a bit about how you can connect with us. Obviously, you're seeing us here on YouTube, but we also have a Facebook page. So if you are not following us on Facebook, please do, as we announce all of our events on there before they happen and create Facebook events so you can keep an eye on when they're going to happen. And we also have a Twitter. So if you have a Twitter, please follow us on there. Feel free to ask us questions through Twitter, and you can also use it as a great way to also stay up to date with our next events. As well as this, we also have an email, which is available here. So this is just a bit of a recap of the plan for tonight, and then we'll get on to the talks. So as I said, Paul is going to be speaking to us first. So he's going to give a 15-minute talk on magnetic fields and the star formation symphony. And then we're going to have 5-10 minutes for questions and then a short break where you can refill your drinks. And then after that, Juliana is going to give us a talk on molecular clouds and supernova remnants for 15 minutes. Again, we're going to have some time for questions from you guys and then another short break. And then hopefully you've got your thinking caps on for the quiz afterwards. So I hope you're all looking forward to tonight. I'm now going to hand over to Paul to talk to us about magnetic fields and star formation. So feel free to share your screen, Paul.
Okay, and let me do. Okay, so welcome everyone, which is online. I probably don't able to see your face directly, but I will be really happy to share with you guys some of the awesome things happening in the universe. So today I'm actually going to share with you about the magnetic fields as a conductor of star formation symphony. So actually I'm a first year PhD student in the Chalmers University of Technology. And I'm really happy to actually able to share with people, which is probably all around the world, about some interesting stuff about magnetic field and star formations. So I don't know if you guys like symphony or classical music, maybe yes or no, but maybe in your mind, if there may be some, what is your most favorite symphony? So for me, I probably can think of some symphony relates to Dvorak, about the New World Symphony, or like also other symphonies, say from Beethoven, etc. So one really fascinating thing is this, how what actually composes this symphony is you have different sort of instruments like strings, you have all the flutes and also other like drums, etc. And then also one of the important character is the conductor. And then when all this combined together, it gives out this amazing harmony of music, and which is just amazing. I'm sure you guys are gonna agree at some point. But now, in this throughout the talk, I'm going to share with you another amazing symphony. Not necessarily really a sound, but it's something I think everyone can witness, which is, let me introduce you the Star Formation Symphony. So here, actually, what I'm going to share is amazing piece of how star actually form in the universe. And see, this is actually a background which is showing the Milky Way, and there's a lot of stars, and these many dark lanes here actually are known as molecular clouds, and it is where the site that new stars are born, and actually where this symphony gonna play out. So in a symphony, we know that there are different movements. So similar star formation actually can be kind of divided into some major steps. So it's like different movement in the symphony. So as I just mentioned, star forms in molecular clouds. And actually here we can see, as this is a schematic picture, it's going from some clouds. And within this cloud, we can see some clumps, which is very dense regions. And actually within these regions, we can actually, where we actually form cores. And actually stars are actually will be forming within these pre-stellar cores. And when during their formations, actually when they start to collapse and accrete materials, disks will form. So you can see actually it's amazing that you go from cores and then they actually form disks and then rotating disks. And also at the same time, they actually start having outflows. And at some point, when they actually, all this thing is more settled, it will become rain to a T-Tauri star system, which essentially become this central pole star here. And possibly these probably start to have some rings, dust rings here, and this ring may possibly become planets. And this is become the stars, and then some planets surrounding about. So this is more like a more, I would say, more simplified and more like a classical picture of a formation of solar mass stars. And of course, that I mean, there are also really amazing details as well, but I'm sure it will not be really able to share all in just one short talk. So, but while all these movements, but what are the key players here in this star formation symphony? So here, there are actually four key players. The first one would be the turbulence. So turbulence is like a very chaotic, energetic gas motions. So I'm showing here is the Van Gogh Starry Night. Why I'm showing this is because recently scientists actually tried to study this, and actually they found that what Van Gogh actually paint out some of the properties of this turbulence. So they have identified this painting, and then they also try to do some analysis and compare to some of the properties, like how energy cascade in the turbulence medium, and they found that they have very good agreements. So it's amazing that a painter actually paint out some physical details here. Another key players I'm going to share in more in depth here is magnetic field. So I'm not sure you probably have seen this, like imagine you have a bar magnet and you have some iron needles. And essentially when you put near them and start going, actually this needle is forming in a very ordered way, which is trying to trace these magnetic field lines. So this is like imagine image here. Another magnetic field, of course, there are two, I would say, really important players. Of course, it's gravity. So it's like, imagine like, this is obviously one of the main or major players that for a star to form. At the same time, there's also what we call the stellar feedback process, which is actually things that is feedback from these protostars like outflow, jet, etc. That's really putting back to the surrounding environment. So these are the four key players that actually will regulate the whole star formation process. So as I mentioned, I'm going to focus on the magnetic fields. But actually, there are two pictures regarding the magnetic fields in star formations. So especially many people is talking about the turbulence and magnetic fields. As I mean, gravity is obviously the ultimate players, and stellar feedback is like also intrinsic events that are happening as the star form. But now when people are asking about, okay, so the turbulence is probably maybe more important or the magnetic field. So if magnetic field more important turbulence, probably is more ordered magnetic field morphology will be observed. Like we can have this non-cold pasta, which I think it would be a good way to represent this. And imagine the turbulence can only like moving along this line, but cannot twist it around. On the other hand, the turbulence is actually stronger than magnetic fields. What you can see is like this water might be mimicking the turbulence, and it's like stirring the whole pasta. Like actually this pasta is like the magnetic field lines has to be going with the flow of this water, or we can actually back to the reality is the turbulence gas motions. So here is two competing pictures, and actually also they're in different stages. They may actually play different roles. So imagine now we are actually sitting in the southern hemisphere in Chile and enjoying this amazing star formation symphony. And I kind of to guide you to this patch of skies, which is starting to see these amazing dark lanes of molecular clouds. Now we're doing is zoom in to this area. What we can see is these gigantic, beautiful pictures, which is showing the Ophiuchus molecular clouds and pipe molecular clouds. Oops. So here is two molecular clouds. We can see is nearby us, which is a distance roughly about 130 parsec-ish. So one of the things we can easily see or immediately see that this cloud is really colorful, while on this cloud is relatively dark. So one thing here is showing that we can clearly see this here. We can see a lot of kind of lines here. So imagine each of these lines back to this earlier symbol of like have these iron needles which trying to trace the magnetic field lines. So these vectors are actually tracing the magnetic field morphology of these two molecular clouds. So, and also, of course, we can try to have a mimic a overall orientation of this cloud. So this is represented by these two white dashed lines. So what we can see is this for Pipe Nebula, we can see this magnetic field overall morphology seems to align perpendicular to the overall cloud orientation, but more parallel for Ophiuchus. And also, as I mentioned, which is really colorful, which is actually showing very active star formations, but here is relatively dark and quiescent. And on the other hand, if we take this black, all these black things are like the mass of the cloud, you can see it is really spatially concentrated for Ophiuchus, but it's slightly more balanced distributed for Pipe. So looking here, I mean, we can use a simple thought, or creative thought to think how, or maybe magnetic field oriented with the cloud may affect this physical properties of this cloud, like the mass distributions, and actually as well the star formation properties. Here, what we're saying is how effectively star form in the cloud, or the star formation efficiency. So of course, two clouds cannot say one thing, but now we now throw in a bunch of molecular clouds. So these are all known as Goldberg clouds, which have a distance within 500 parsec. So this, for example, we have Taurus, Corona Australis, Orion, B, and etc. So now on each of these, we have many of these black dot lines are actually tracing the magnetic fields. And here I take a dashed line here, which is the cyan dashed line. Here I'm trying to give a overall or mean direction of these magnetic field orientations. And of course, the white dashed line here is showing the overall long axis orientation of the molecular clouds. So you can see, of course, it seems to us they're all sort of orientation. But if we look closely, it seems that clouds is either oriented close to really perpendicular to each other between the two lines, or almost parallel to each other. So these actually show us that cloud seems to align either normal or close to perpendicular to the magnetic field directions or parallel to the magnetic field directions. So one more things we can study is how they affect the physical properties. So imagine we can squeeze this cloud, mass of the cloud, towards the white line. So imagine the line, now to crossing the cloud parallel to this line, and this becomes like one line mass. And then we divide this dashed line into half and compare how much mass between these two halves. So this we can define as we call a mass ratio. So how this may actually, would there be correlations with how the cloud may align with the magnetic field orientations? So now we can imagine transforming this into a little bit data points. So we can see on this plot, two plots, essentially having the same x-axis, which is the orientation with the cloud, and the mean of magnetic field directions, like I showed in the last slides. And here the y-axis here is imagine we squeeze the cloud into one line and then compare the mass of the two halves and then divide them between each other, we get a mass ratio. On the other hand, we can also study the star formation efficiency, or like based on like the star formation activities. Immediately we see a correlations here. Of course, we can also see there's some scattering, but we can see overall there's a correlation that for clouds that have a larger difference between the magnetic field orientation and the cloud orientation, they have a more balanced mass distributions and a lower star formation activities. On the other hand, you can see cloud which is having orientation almost aligned with the magnetic field directions have a less balanced mass distribution, or like a very concentrated mass distribution and a much higher mass star formation activities. So how possibly we can explain this in terms of magnetic field guiding the turbulence and gravity? So imagine this, each of these lines magnetic fields, like this really ordered non-coke spaghettis. And now we have this like gas and gravity playing against each other along the field lines. And of course, due to Lorentz force, which is that it is really hard to really collapse in the perpendicular. So it will be, the gas motion will be largely moving along the field lines. So of course, then either the gas can actually accumulate, or gravity more like pushing the gas to each other. Then you can form these two clouds, which is either parallel or perpendicular to the magnetic field lines. This is actually what we observed just now. And now, if you imagine, if you want to really break it, so you can consider this area here. This has a larger area, which is like more spaghetti than this, you can imagine. So you want to crush them, it will be harder for this cloud than this. So you can, as one of the things, it is really essential for the molecular cloud to really fragmentate or break into pieces to form stars. So you can imagine this actually face a smaller, or we say resistant in breaking it, and it is more capable to fragmentate and actually form stars. And actually these actually see from here. So I have a more active star formation and more concentrated mass distributions as this. So I guess now I will give a summary of actually what I've shared. So from here, I'm actually trying to share out that star formation is amazing. And one thing I'm trying to actually show you is magnetic field actually play an important role in star formation in a very large scales, and actually go from the cloud even to the star formations. So it's actually affect how the mass distributes in the molecular clouds, and also how effectively stars form in the cloud. Of course, this is actually tip of the iceberg, and there's a lot of more stuff happening with magnetic field and star formations. And of course, there's still a lot of unanswered questions and things we need to know to understand the link between magnetic field and star formations. So actually, this is pretty much my talk, and I really want to thank so much. And before that, this is actually one of my experience of how connecting astronomy and music. So I mean, it's about the star forming symphony, and this is one of the things that I really like, which is the Planet orchestral shoots by the host. And thank you very much for, again, yep. And I would really like to start taking questions.
Okay, that was a great talk. So I'm just checking now, and I don't think we've received any questions yet. So we've got none so far. So I'll give a couple of minutes to the audience to see if anyone has any. So I don't know that much about star formation, but I've heard that star formation regions, I'm asking a question of my own here, are different for forming both low mass stars, so stars that are, going down a slightly different evolutionary route than like massive stars. Obviously, they're very different later on in life, but I've heard that they form in different regions to begin with. And I was wondering, do you think that these different alignments in magnetic field could be in some way connected to then the formation of those different types of stars? And could you expect to see more massive stars in one type of magnetic alignment and more low mass stars in another type of magnetic alignment? So I was wondering if you had any thoughts on this, or if this is possible.
Actually, these are very interesting and good questions. So I think I can try to give it. So actually, there's something that probably can inspire some of the people. So in many cases, we also know that massive star formation may also actually form in places that is really having star clusters. So one of the interesting thing is we found that in here, for example, Corona Australis, Ophiuchus, Aquila, they actually all are regions that actually have like clusters formations. And most of these clouds are actually parallel to the mean magnetic field orientations. But for example, Taurus, for example, Lupus 1, they have relative more dispersed star formation, which is not strongly clustered, which actually they have cloud orientation more perpendicular to the mean magnetic field. So it could be, I think there should be suspect there could be some relationship between how like the mass spectrum in the cloud relates to the magnetic field orientations.
Okay, great, thanks. Yeah, it'll be interesting to see if developments are made on those sorts of ideas in future. And I hope that you're working on answering some of those questions for us. So we have now got some questions, which is great. So the first question I'm going to ask you is from Sarah, and it's, how does having multiple dust cloud components along the line of sight affect your findings?
This is actually very interesting and nice questions. How different dust components may affect the star formation. I mean, I hope I get the question correct. I don't know if I actually get that. So one of the things is that you have like different components that just lying along the line of sight, which maybe have like actually different contributions. And of course, this actually is something we actually need to have if we have more 3D informations. So actually one thing here is we actually assuming this is a 2D, I mean, cloud actually is 3D, and we actually project to 2D here. And we're assuming like they are like essentially one elongated structure. But now if there's different components, one thing is we actually have to dissect this cloud into different components. For example, using different distance, or like using different criteria, and also being more localized and compare this again. I think this is something that's worth interesting to study as well. And I think it is a very good question that actually point out that this actually has some further works that need to be done actually. Yeah, thanks.
Okay, great. And we've got another question from Anders. So that is there a particular time period in star formation where the magnetic field is more important than the other factors that you mentioned?
Actually, my personal answer, the magnetic field are actually mostly quite important from cloud down to even a core scales. So remember, we have this 6 movement during the star formation symphony. Actually, I think magnetic field is essentially playing a quite crucial role from this movement 1 down to, always say, even to movement 5. So it's more like magnetic field seems like to me is like a conductor. So conductor here is like you're actually kind of regulating different part of the whole orchestra to play out this harmony music. So imagine magnetic field is like guiding how the turbulence and the gravity interact with each other, and also the feedback, and leads to the whole star formation process. So I think at some point I would say that is quite crucial in many of the steps.
Okay, great. I really love the metaphor that you've brought together with this symphony. I think that's a great way of explaining it. So I can't see any more questions that we have. So I think just give it a couple more seconds, but yeah, none other ones are showing up. I just want to thank you again for a great talk to begin this evening. So I think that we're now going to go for a short break for 5 minutes, and then we'll come back at around past to listen to Juliana for her talk. So yeah, I hope everyone at home has a good break. Go refill your drinks, get some more snacks. and I'll see you all in 5 minutes.
Thank you.
Okay, great. So we're now back because it's been 5 minutes. So I hope you all got your drinks and your snacks. So we're now going to listen to Juliana and her talk on molecular clouds and supernova remnants. So I will hand it over to you.
Hello, let me show my screen. Yes. Okay, hello everyone. Well, apparently I'm the last speaker of the season, not just of today. So it's kind of an honor to conclude this Astronomy on Tap season. I hope you will enjoy the talk, and I just want to want to thank all the organizers, not just for giving me the opportunity to talk today, but also for making all these efforts in putting together these events that are very, very nice, and I usually enjoy very much. So today with you, I want to discuss the interaction that occurs between molecular clouds and supernova remnants and how this is shocking. So before starting, I would like us to be on the same page. So I'm going to revise some of the terminology that I'm going to use during the talk. Although Paul has already did an amazing job in explaining us all the key aspects that I'm going to use in my talk. So first, I will use a lot the word molecular clouds. As Paul has already told us, molecular clouds are very dense regions in the sky. They are made basically of gas and dust. And when I say dust, I refer to very small particles that have a kind of a rocky interior, or a rocky core surrounded by a layer of ice. And as Paul said, molecular clouds are usually called stellar nursery because it's in this place that stars form. Then I will also talk about massive stars. So when I will refer to massive stars, I will be talking about stars that are at least 8 times heavier, more massive than our sun. Then I will also talk about supernova explosions. That doesn't really requires a lot of explanation, but basically when a massive star reach the end of his evolutionary path of his life, so basically when a massive star dies, it does it very violently, and basically it collapses under its own gravity and it explodes. What left behind, it's a supernova remnant, so it's basically this shell of energy particles that is expanding into the surrounding medium. Now that we more or less know what we're talking about and we are on the same page about all the words that we're going to use, let us understand what is, I want to discuss with you what is the problem that I'm trying to work on with my research, with my everyday research. So basically, when we take an entry class level in astronomy, or even when we study in high school, when we are told how a massive star form and evolve, we're basically presented with a picture that is very similar to this. And that tells us that we have basically a molecular cloud, that at some point the densest part of this molecular cloud will collapse and form what is called a protostar. And this protostar will first be surrounded by gas and dust, then with several steps, it will dissolve this material around it, it will dissipate this material around it, and we are left with a normal star as we are used to see in the sky. And this star will evolve depending on its mass and will eventually explode as a supernova and leave behind either a neutron star or a black hole. In principle, from this picture, it seems that we have got it all. Everything is clear. We don't need to research anymore. But actually, this is not entirely true, because although we know with certain details some part of this picture, there's a bit of dust under the rug here, because we don't have really a clear idea how we get from a molecular cloud to a protostar, at least in the case of a massive star. We do have a recipe in a sense, and this is the one that Paul has already told us very nicely. So we have a dense core, this dense core collapse. I will go very fast because Paul has done it very nicely and I cannot really make it better. So there's a core, the cores collapse. We will have this system that is made of a protostar and a disk. This protostar can eject a lot of outflows and jets, so the concur on dissipating the dust and the gas around. Eventually, the disk becomes tinier and tinier, and we are left behind when all is dissipated with planetary systems like the one we are used to. Now, as I said, this kind of works very well, but only if I want to build up a star that is no more than 20 times more massive than our sun. If I want to build up a star that is heavier than that, there are some problems that we encounter. For example, we don't know yet whether we have a single core that collapses and forms a single star, or instead, if I have some smaller cores, then collapse, and then these stick together to form a massive star. Another question that we ask ourselves, and for which we don't still have a certain answer, is in the case that is true the first scenario, will the star form a system with a disk around, or the material will fall on the star in a different way? So all these are questions for which we don't really have a clear answer yet, and there are still work in progress in science. So you can say, well, it's very simple to solve. You have very powerful telescopes. You can take one, point it toward a certain portion of the sky in which you know that a massive star is forming, look at it, get all your answer, and this is done, easy peasy. It's actually not that simple. The first problem that we encounter, as we said, is that these massive forming stars are embedded in this cocoon that are very thick, made of dust and gas, that don't allow the light from the central object to reach us, which means that basically we are blind. We cannot pierce into the core. And this is the first problem. It is basically probably the most important one. Then another problem is that although it's weird to say that in space something evolves very quickly, massive stars, it seems they are they have a lot of mass, they evolve relatively faster than other objects. And it's difficult to go in the sky and pick at the exact spot in which there is the exact phase that you want to observe. Least but not last, or last but not least, these objects are usually very far away, which means that I need the telescopes that allows me to really maintain a certain level of details when I look at it. It's more or less the same when I have a photo camera. I want to observe an object that is far, so I zoom in, but at some point my image is not neat anymore. It's not very clear, so I lose in details. So in my research, instead of going to study the stars that are forming, I go a little bit earlier than that, and I study what they're called, as I say, molecular clouds. Now, this action is basically what I'm trying to do is to ask myself, what is the first instruction that I need to follow if I have to build up a recipe to form a massive star? So the question is, how can I start massive star formation in molecular clouds? There are several theories about this. The one that I studied, so that I'm going to discuss with you today, is called the cloud-cloud collision. This is very simple. It's nothing more than a collision between clouds. So I have two clouds in the sky. These are the two clouds. They move, there are some point they encounter each other, and they collide. And at the interface of this collision, they compress the gas so much that they can effectively form a very, very dense spot, and this spot can eventually form massive stars. So, in my research, I do know where I want to look in the sky. The point is that how can I really see this mechanism in the sky? Well, luckily for us, toward the end of this sketch, this process, at the shock interface, at the compressed interface between the two clouds, it develops what is called an interstellar shock. Now, if I have to say in really few words what an interstellar shock is, I would say that it corresponds to an interstellar slap in the face of a molecular cloud. If I have to give you a picture, a visual idea of what an interstellar shock, I would say there is something similar like this. something like this. If we imagine that the guy is one cloud and the wall is another cloud, it's just really a collision of the two. So now that I know what I need to look for, how can we detect this interstellar shock in space? Well, the point is that when shocks occur in space, some molecules that usually we don't see normally in molecular clouds start to appear. One of these is called the silicon monoxide. Now let's see together why this molecule appear when there's a shock. So as we said, molecular clouds are made not just of gas, but also of dust. These dusts have a core, and the core is surrounded by ice of several molecules, mainly water. In this core are locked some atoms that stay in the core unless there's something that release it. This something that destroy the core and release these atoms is a shock, for example. So the shock occurs, the dust is destroyed and release in space these atoms. Amongst these atoms, there's the silicon. This silicon, that now is free, is able to react with other atoms in the gas phase. For example, oxygen. They stick together, they form a molecule that is called silicon monoxide. Now, it's easy to see from here that if I don't have a shock that destroys the dust, I won't be able to see SiO. So basically, no shock, no SiO. So at this point, just to do a recap, I know what I want to see. I know the tool that I need to identify it. The only thing that I need to do is to look in the right spot. How can I actually see where to look? Well, this is related to where cloud-cloud collision can occur. So the first scenario is that I have two clouds. These two clouds are on the galactic plane, they move, and while they move, they encounter each other and they collide. Another possibility is that a supernova remnant expand with its shell into the surrounding material, it sweep up a lot of molecular material like dust and gas and push this filament of material toward a cloud that is nearby. In my research, so I started my PhD looking at spots in which the first scenario was occurring, or I was hoping that the first scenario was occurring, but now I'm more oriented toward cloud-cloud collision that have been ignited by the presence of a supernova remnant. So this is the spots in which we're going to look. We're going to look into a region of the sky that have a molecular cloud nearby a supernova remnant. We found one of these clouds. It's called G034. Sometimes I call it cloud G because it's simpler. And this cloud is located, so the cloud is highlighted in this picture with the black ellipse, while the supernova remnants nearby, that is called W44 and is very well known, is highlighted in blue in this picture. Now, if we take a closer look at the cloud, we see that toward this cloud is happening exactly the cloud-cloud collision we were discussing about, because the supernova is pushing some material that is highlighted in blue in the picture. This is encountering the red material that is associated with the cloud, and these are basically colliding. Toward this spot highlighted as a yellow square in here, we are seeing exactly the SiO we were discussing about. So just to give you an idea, what is happening is that if we consider our cloud as a sandy shore that we see on a beach, and the material pushed by the supernova as a sea wave that forms in deep water. So this is the cloud, this is the material that approached the cloud. So this is the wave. The wave encounters the shore, there is the cloud, plunges into the shore, breaks, and form this little foam that we are seeing in the movie of the beach. This little foam is equivalent exactly to the SiO that we see in space toward this cloud G035, and that we are seeing in color scale in the movie on the left-hand side, while in white shadow is the cloud. So basically, We have seen what we wanted to see. We know that is there. The real big question is whether this is going to form massive stars. This is a work in progress. So I hope to have an answer by less than a year. And so please stay tuned, because for the better or for worse, we are going to have an answer. So if I really want to prove that cloud-cloud collision are important to form massive stars, one object is not going to be enough. So basically, we need to look for other objects, and this is going to do with Shrek, which is not the one. So Shrek is a large program that is going to use an antenna like this that is located in Arizona, and it's going to look for 27 objects, supernova remnants, and to look for SIO around. These are some of the supernovae that we are going to observe. The project has already started, and we have observed this supernova remnant, which is IC443. And toward this, we have seen SIO, which is quite extended, as you can see from the caption over there. And we have also observed this supernova remnant, which is W41, and that where you can see 3 spots of SIO. So this tells us that maybe cloud-cloud collision is not so rare, and that this may be important to form a massive star. So I leave you with my summary. Sorry, I went a bit over time. And I thank you very much for your attention. And I just want to tell you that today is Asteroid Day. Thank you.
Thanks so much for a great talk. That was really good. So we do have a question already from the Slack, from the chat channel, which is great. So I'll ask that for you now. So Eshan has asked, how has the silicon been formed after the collision? Is this a chemical reaction or nuclear? How about the oxygen? So that's a bunch of questions in one for you.
Yeah. Basically, we start from a material that is already molecular, so we are not forming the atoms, we are forming the molecules. So that, of course, that in the supernova explosion there will be some ionization, and you can remain only with the core for the atoms. So there are going to be a lot of free electron going on. But in the cloud, we start from conditions that are already molecular, so we are not binding up atoms, only molecules.
Okay, great. So currently we don't have any other questions from the chat, so I'll just ask a question that I came up with, which is a really basic one, but just in case anyone in the audience was wondering this at home. So obviously you mentioned that SIO is a good probe of cloud-cloud collisions because it is a shock tracer. And I was just wondering, are there any other molecules that you might also be interested in looking at as a shock tracer as well?
Yes, of course. So SIO is only one of the many, and it's important because it's unique. As I said, no shock, no SIO. Another one is, for example, molecular hydrogen. Some transition are excited because of the shock, so you know which frequency to look at, to look for, and you know that it means there has been a shock. Another shock tracer that comes to my mind is, for example, methanol, but instead, as opposite of SIO, this is not unique, in the sense that usually is also present when we don't really have a shock, because it can be really is located in the ice of the dust, and this is much easier to release. So there are other mechanisms that can release methanol, but usually when there's a shock, the methanol is more abundant. So we know that there may be something else going on. So yes, definitely there are other shock tracers.
Okay, great. Well, it sounds like SIO is the best one to use though. So we do have another question, and this is from, I'm really sorry, I don't know if I'm going to pronounce this name properly, so I apologize in advance, but Thiz or Thish. But I'll ask the question. So the question is, what mechanisms cause a protostar to eject mass in a certain direction or preferred direction?
Yes, this is what we call a molecular outflow, or basically a jet. And the point is that there's the disk, and since the angular momentum needs to be kept the same, the star ejects some mass in this way. So it's always kind of perpendicular to the disk. That's why it's a matter of keeping the law of physics valid.
Okay, and we actually have another question from the same person. So this question is there a typical false alarm case where SIO is detected, but there isn't any cloud-to-cloud collision triggered by supernova remnants?
It may, because as I was discussing, outflows are also little tiny shocks in which there can be a lot of SIO in there. But usually we are able to distinguish between the two scenarios, because usually in cloud-cloud collision, the emission that we see is much more extended than in the case of the outflow. And also the velocity at which the gas goes is relatively smaller in the case of cloud-cloud collision. So it's difficult, but we can in general differentiate between the different scenarios.
Okay, great. Thank you for all your answers. So we don't have any more questions in the chat channel. So I just want to take a moment to thank you again for your really great talk and all the animations and everything. It was really, really good, clear talk, and to actually thank both of our speakers for their talks. So we do actually have another question. So I'll give you this before we go for our break. This is a question from Anders, and this says, as cloud-cloud collisions, can they also be detected by electromagnetic radiation?
Well, we detect the lights, so that's what we do. We basically detect the lights, and it's really the same mechanism for which we have all the light that comes from the supernova. We pass it through a prism, we separate into the different frequencies, and we pick the frequency at which we know we are looking, we are hoping to see. For example, I know that the SIO is around 87 gigahertz. So I point my detector over there, and I only collect that particular kind of electromagnetic radiation. And this tells me that whether there is or there is not SIO. So yes, it comes all from the electromagnetic radiation.
Okay, so I think it was followed up with a comment of, is this like X-ray? But I think, as you've already mentioned, you tend to look at things slightly longer wavelengths, such as millimeter waves and radio waves, yeah?
The point is that not, when you have a telescope, it will not look at all the possible kind of lights that you have in there. You really need to select which telescope to use, how to build it, because different lights means that we need to have different mechanisms to collect it.
Okay, great. Thanks so much for your answers. As I was saying, I just want to thank both speakers for these brilliant talks that you've both given tonight. So you guys can both relax now. And in fact, if you want, you can even have a go at some of the quiz questions we're going to have later. So I'm going to switch over to our break slide because we're going to take a 5-minute break, and then we'll be back in 5 minutes at around 58 past for the quiz. Okay, and so we're back. So I'm going to stop sharing my screen and I am going to hand you all over to Franz, who is going to talk to you all about the quiz for this evening. So over to you, Franz.
Radio, let's get the quiz started. Oh, here we go. I believe the link to the quiz has been posted in the chat. So let me quickly share my screen. And here we go. And in case you see something that says the quiz is not accepting answers, then you may want to refresh your browser window because I now opened the quiz. So today we have a bit of a mix of questions that relate to the talks you heard. And then we have a section that relates to most recent events because we want to put a little bit of awareness on equity also in academia. So if you have that quiz up on your screen, or maybe you see it in the live stream. So first of all, we'd like you to put in your team name, because by the team names, we'll in the end figure out who is the winner. And what would be nice, or what you actually need to fill in, is whether there is an astronomer on your team, because we will judge the different teams differently, whether they have an astronomer in their team or not. You know, there will be two categories of groups. All right, so what are the questions? Let's get started. The first one is, the first section is mostly on different beautiful images, and you're supposed to name them. The first one is, what is the name of this beautiful supernova remnant? Is it either the Crab Nebula, so supernova 1054? Is it Cassiopeia A? Is it N49, or is it supernova 0509? I'm sure you know all those cryptic names like I do. Then we have the next one is this beautiful picture of a star-forming region. And here we now have, is it either Kepler's supernova remnant, so supernova 1604? Is it the Horsehead? Is it the Crab, or also Crab Nebula, or is it the Carina Nebula? Next question. We have another beautiful star-forming region in many different colors, as you can see. So is it the Monoceros R2? Is it the Pillars of Creation? Is it Mystic Mountain, or is it the Horsehead? Moving on, another beautiful star-forming region. Here again, we have four answers. Is it either the Pillars of Creation? Is it the Eagle? Is it Carina? Or is it supernova 0509? And again, we have another star-forming region, which looks extremely fantastic. Is it Orion? Is it the W3 star-forming region? Is it Monoceros R2? Or is it the Crab? And we go on to, when was the most recent observed supernova event? So what's the most recent supernova event that we actually saw? Did we observe that in 1820? Did we see that in 1900? Or most recently in 1985? Or was the latest one we saw in 1604? After that, how many supernova remnants have been observed in the Milky Way? So supernova remnants are those leftovers from the explosion of a massive star, if you recall from the talk. So have we seen 383 in the Milky Way, our own galaxy, or have we seen 1,125, or was it 57, or do we only know about 9 of those supernova remnants? Moving on, we go to the expansion velocity of the expansion shell in Cassiopeia A. So that's the velocity. So once the star explodes, you have this big shell moving out in space. And here we're asking at what velocity is this material moving outwards from the explosion? So is it either between 4,000 to 6,000 kilometers per second, or is it a factor 10 slower, namely just 400 to 600 kilometers per second, or yet another factor 10 slower, 40 to 60 kilometers per second, or a tiny 4 to 6 kilometers per second? And I think here are two more questions regarding star formation and supernova explosions. So the Next one would be the star formation recipe. So that's the recipe that Paul talked about. Which of these four does it not work for? So does it not work for stars less massive than the sun? Does the recipe not work for stars more massive than the sun, but less than 20 times the mass of our sun? I think Gian actually spoke about that too. Or is it not working for stars more massive than 20 times the mass of the sun? Or does it actually work in all kinds of stars? And that question makes no sense whatsoever. You pick. And the last one that relates to our talks is supernova explosions. Do they happen when a massive star forms, or when a massive star cannot continue thermonuclear reactions, or when a massive star exits the main sequence and becomes a red supergiant? Or do those supernova explosions only happen in low mass stars? Now, moving on to the next block that we'd like to ask you about. So this is, I guess, mostly about awareness of equity and equality in academia and, of course, globally. So here we go. Which European country has the highest percentage of female researchers? Is it A, Albania, the Netherlands, the UK, or is it Sweden? So the highest percentage of female researchers. Next one, I guess that's one for all the Swedes watching. When did a woman first graduate from a Swedish university? Was it already in 1636, or was it 200 years later in 1871, or in 1910, or was the first woman to graduate from a Swedish university only about, 67 years ago, in 1958? Now moving on to more global numbers. What percentage of researchers worldwide is female? So is it just 11%, 1 in 10? Is it 29%, 37%, or close to half, 46%? So what's the percentage of researchers, female researchers worldwide? Okay, going now to space travel. Who was the first Black woman in space? Was it A, Mae Jemison? Was it Sally Ride? Was it Dana Ullery or Eileen Collins? And I apologize if I mispronounced any of those names. And then the last of our questions today is 13% of the US population is African American. So those are numbers from 2010. What percentage of physics bachelor degrees was earned by African Americans? So was it 15%, 10%, 3%, or was it less than 1%? So now I'll give you, say, another 4 to 5 minutes to go through the questions and answer as best you can. And when we're done, I'll close the question part and I'll give you, of course, the answers and the statistics, and we will hopefully have a winner. So bear with me, or happy answering. I hope you're not Googling. Of course you can, but please don't. So in 4 minutes, time's ticking. And it looks like we have 12 responses. So 12 people have so far filled in the whole questionnaire and submitted it. So we have all these beautiful star forming regions of which you want the names. Go through them, enjoy the pictures. And then another star forming region. And yeah. So we have another 3 minutes, still at 12 responses. Interestingly, I have no idea how many teams actually subscribed. Maybe all 12 that actually signed up did already submit, but we'll give you another 3 minutes. Oh, more people moving in. Don't panic, 3 minutes left. 1 minute to go. But we're at a constant 13 submitted forms. Are we going to make it 14? Yep, here we go, 14, 15. All right. It's good we're waiting. Okay, time's up. Last 30 seconds. All right. I would say time's up. 10 seconds more. Okay, 10 past 9. Let's see, let's close the form. If you haven't submitted, press the submit button yet, even though if you haven't answered all the questions, press now, press now, press now. And we'll stop accepting responses. And here we go. So we have, what do we have? We have, okay, 8 points. So the median is that 8 teams got, no, the median is 8 out of 50. So 15 questions, 15 points. We have a median of 8. So let's see, what are the correct responses? So let's see, team name. Who won? Is the first one the one who won? Can somebody not? Because I don't understand this thing here. I guess Sid won. Is that what this is?
So you should be able to find a spreadsheet if you click one of the buttons. I can't remember which one, but that might tell you if you try and export all of the marks, who got the most marks.
Oh no, that's not the one.
So
let me try and figure that out.
There's a Excel button at the top that says create spreadsheet. If you go up to the 15 responses, and then there's like a little Google Sheets thing. It looks like an Excel icon.
An Excel icon.
So if you scroll to the very top of where you are at right now.
Okay. Oh, that one.
Yeah.
Ha. Okay. So we have the highest score is apparently Holly.
that's actually me. So I think you should go to the next person because I was just playing for fun to play along with everybody.
Okay, here we go. So then we have a draw between Mark and Amy and Falköping Astro. Okay, so that's an Astro group. No astronomer in the group. Mark and Amy, they do have an astronomer in the group. So then I would say Falköping Astro without an astronomer is clearly the winner. And Mark and Amy are the Astro group winners. Excellent. So I would suggest you send us an email and then we'll figure out how to get prices to you, or you just rock up at the next physical event. But as I promised, I was going to give you the correct answers. So the first supernova remnant, that was Cas A. Then we had the star forming region, that was the Horsehead. So if you don't remember the pictures, so this is apparently Cas A, and that's the Horsehead. Then we go on, we have the Mystic Mountain, are these guys. Then we have the Pillars of Creation. Well, one could actually almost tell. Then we have that star forming region, which is Orion. Then the most recent supernova event was in 1604. So that's 400 years ago. Then we have how many supernova remnants have been observed? This was the first answer, 383, and 2/3 of all answers, 2/3 of all people got it right. Then the velocity of the expansion shell is an amazing 4,000 to 6,000 kilometers per second. Half of everybody got that right. Then we have the star-forming recipe does not work for stars more massive than 20 times the mass of the sun. Again, 2 out of 3 people or teams got it right. Then supernova explosions happen when a massive star can no longer continue thermonuclear explosions, or reactions, not explosions, reactions. And then here we go. Albania has the highest percentage of female researchers, but only two teams actually picked the right country here. When did the first woman graduate from a Swedish university? That was in 1871. Then what percentage of researchers are female worldwide? So that's about 1/3. Who was the first Black woman? That was Mae Jemison. And then we have, so 13% of this population is African Americans in 2010. And in total, 3% of the bachelor degrees were earned by African Americans in the US. So here we go. That's the end of our quiz today. Like I said, the 2 teams that won, send us an email. We'll figure something out. And with this, I will stop sharing my screen and I'll pass back to Holly, who will conclude the session.
Okay, great. Thanks so much for a great quiz. I mean, I really enjoyed it, as you can tell from looking at the marks. So I'm just going to share my screen quickly, just to sign you all off for the end of our session today. So I hope you all enjoyed our 3 online Astronomy on Tap sessions that we've had over the past few months. So we're now all going to take a summer break, and I hope you at home are looking forward to your summer break as well, even if it's more of a staycation this year. And I hope you all have a great summer break, and we're hoping to get back to you with our return in September. And if you keep an eye on our Facebook and Twitter, we'll be sure to tell you if that's an in-person event or an online event. So keep an eye on all our social media channels, and that's how you'll be able to find out where we will be. But we will be back in September with some exciting talks and new speakers for you guys. And I just want to say a massive thank you to everyone who's been there for us, listening to us online, and for all the technical difficulties we've had and coming and joining us in this new format that we've had. And I hope you've enjoyed it as much as we have. So I hope you all have a great evening at home and keep drinking, or if you've had a few drinks already, just have a great evening. And thank you from all of us here at Astronomy on Tap in Gothenburg.